This is my Physics 1101 Lab 1, Motion with Constant Velocity by Jacob Cook. Observe versus computer model motion. For this lab, I will be assessing the motion of an object that is moving at constant velocity. I will then compare this data to a computer model. I'll use Tracker for the observational data and GlowScript Python for the computer model data. My purpose is to compare the observed motion of a pool ball compared to a computer model with the same parameters. So models and fundamental physics principles. For the observational model, I'm using Tracker, and for the computer-based model, I'm using GlowScript Python. So I'll be using the position update formula, which is final position equals initial position plus the average velocity times change in time. Since there's constant velocity, there's no net force because acceleration is 0. My observational data does experience a negative acceleration, signaling there is a force acting upon it. I took this into account and adjusted my computer model. The result of the lab. In observation of the pool ball, it is clear there is a small negative frictional force acting against the pool ball. Under the premise, the orientation of the x-axis is facing in the positive direction. Initially, the observed velocity was higher than the computer velocity due to the force exerted by the pool stick. While the computation stayed linear, the observational data of the pool ball exhibited a slight negative acceleration. In conclusion, while the friction was low, there was a small frictional force that acted against the motion. I determined this is not statistically significant, however, due to the observational and computer model graphs being similar. So here's the system of the cue ball. You can see that the force of gravity is acting on it as well as the normal force, and there's a slight force of friction, making the net force not entirely 0, but very minimal. Okay, so here I will show you the motion of the pool ball. You can see that it moves with relative constant velocity. So this graph shows the position versus time graph of the motion of the pool ball. You can see that the tangent line stays roughly the same throughout, except towards the end it starts decreasing its slope, meaning that the velocity is slightly decreasing. This velocity versus time graph better shows that fact. You can see as the time goes on that the velocity nears more around 5 compared to when it initially started with 7.5 meters per second. So here's the code I used for the computer graph. So when I run this module with the exact same parameters as the pool ball, it shows the motion. And this has 0 net force because I was able to neglect friction using the computer model. So here's the graph for that. It shows a constant velocity. And so here's the velocity. It's roughly a little above 0.64. And here's a comparison between the observed and computer model position versus time. As you can see, they're roughly the same, where the computer position stays completely linear the entire time. There's a slight negative acceleration on the observed position, and this is due to friction. So here's the computer model assumptions. The pool table coefficient of friction is 0.06. The mass of the pool ball is 0.156 kilograms. Using the equation, the force of friction times the coefficient of static friction times normal force, I figured out that the force of friction was 0.091728, and friction should be negative in this case because the vector is, that vector is pointing in the negative x direction. And here's what it would look like if I were to apply this to the coding. Okay, so what if my axes were oriented in different ways? So changing the axes would just change the direction of any vector quantity like net force, acceleration, velocity, etc. So what your observation could be predicted in the computer model when. So not including friction or air resistance, the two forces acting on the pool ball would cancel out, the force of gravity and the normal force acting on the table. So here's some possible sources of error. The coefficient of friction on the pool table could be different from the standard COF. masses of pool ball could be different. The perspective of the camera could be affected by the observational speed. And I use the average velocity of the entire observational motion of the ball, where I should use a short period